got 3 talks today. I'm chairing it. I'm Stuart Haszeldine from the University of Edinburgh and one of the co-investigators in the UKCCSRC enterprise. So we've got 3 talks, 15 minutes each, and then 5 minutes questions. And then we should have a little bit of time left at the end for any more serious debate. So first of all, we'll go in the running order in the programme. So first of all, Yihuai Zhang from University of Glasgow has made a PhD study at University of Curtin, been working in Glasgow for about 3 years now, and he's going to talk to us about dynamic storage of CO2, migration-assisted trapping in carbonate rocks. So over to you.
Okay, so today my topic is about the dynamic effect in CO2 storage. So it's insights from port scale. Okay, port scale. So I'm Yihuai, and I'm a lecturer in geoenergy engineering in James Watt School of Engineering and University of Glasgow. Okay, so the first, so we'll talk about, okay, so what we are, who we are. Okay, so I built this research lab in 2022. Okay, the photo is the first 2 PhD students left hand side is Amy, right hand side Josiah, my first 2 PhD students. So the main contribution of the PowerPoint presentation is from them, okay? And the 3 main research area nowadays we are doing is a physical, chemical, mechanical process in fluid-solid interaction in sustainable geoenergy. Also, we're doing an advanced simulation method in porous media materials. Also, now we're doing some lunar and martial soil mechanics. So that will do. So that is the main flow chart, what we have. So meaning, because I'm a petroleum background before, nowadays we all go into the net zero energy, right? So which are based on fluid rock interaction. Okay, we have a different lab method. Okay, we have SEM, we have microCT. Okay, we have ultrasonic, we have the UCS, a different test. Then this can we have a simulation method built in a digital rock. Okay, so we have quantify the different mechanism into CO2 storage. Okay, and also this can be application not just CO2 storage, as geothermal, nuclear waste disposal, or also the hydrogen sequestration we store some advanced pore scale fluid dynamic studies. So that is what we are. Okay, so we have this facility in University of Glasgow. We built the advanced in-still core flooding facility in Glasgow. Well, nowadays in UK, they have several universities, and in Edinburgh and Imperial College, Manchester, we also Strathclyde, we all have these facilities. Okay, so this facility can simulate the real reservoir conditions, high pressure, high temperature. Okay, we can simulate different high pressure, high temperature condition to the real reservoir. And we can use the microCT, we can use ultrasonic, and use also the synchrotron imaging to monitor how exactly change inside the rock. So that is the main purpose of this facility. So we can observe that, instantly observe that, okay, what happened actually happened inside the rock. So this can be application into the carbon dioxide storage. Okay, so this is a photo of what we have in the University of Glasgow. We have the X-Radia 620, the Versa. Okay, we have the what we have? We have the core holder. Okay, we can see what's going on here. Also, we move our equipment to the diamond. Also, this UKCCSRC funded this project. Also, diamond funded. So we conduct this experiment. Okay, inside the diamond light source BM9 I13. Okay, so let's go back to our topics. What is the dynamic effect in storage? Okay, there are a lot of dynamic effect actually in storage. So what we're doing, the following research, okay, in this project. Okay, first we're doing the whole modeling of swirling effects and fracture probability in the CO2 shale interaction. Okay, we also are doing the temporal dynamics of the reactive CO2 flow and trapping in carbonate rock. Okay, so we also nowadays conduct some the nonlinear Darcy flow in CO2 brine dynamics. Okay, so this will not be covered in this presentation because the analysis is still going. So we only talking about the first whole modeling of swirling effect in shale and also reactive CO2 flow and trapping in carbonate rock. Okay, let's continue. So what's the swallowing effect and fracture permitting CO2 storage in shale? Okay, the shale is important in oil and gas industry, as we know. The now shale gas in USA, the change all the energy market in the world. They have the flurry of the shale production, right? So shale also can be for the storage for CO2 because they have capacitive storage. The storage mechanism is different with sandstone or carbonate rock. It has the adsorption mechanism, like shale gas, it can absorb it into shale. So CO2 can be adsorbed into the shale. This is one application where we need to care about CO2 and shale interaction. Another one, shale role can be as cap rock, okay? Because in oil and gas industry, a lot of the reservoir were cap rock, it's shale cap rock, right? So the shale also can be a cap rock for CO2 storage. We will have abundant oil and gas field, okay? We still have the shale cap rock. Okay, we inject the CO2 inside. Okay, the shale can be a cap rock of the CO2 storage side, right? So they have the unique crack size compared to sandstone, other different rocks. The shale, it has swallowing effect, okay? When the CO2, it can absorb into the matrix, the shale matrix, it can swallowing, the shale can swallowing. So this will be very interesting for the CO2 storage because it means if we have a leaking road, such as in the cap road, the cap road have a shale cap road, there's some leaking road, some small fracture. When the CO2 are dissolved onto the shale, inside the shale, the small fracture can be closed, maybe. Okay, so this can be stop the CO2 leaking. Also, it can also affect adsorption trapping if shale can be a reservoir. So that is why we need to fully understand how the CO2 shale interaction, okay, can be the swallowing effect can affect the permeability, can affect how much adsorbed inside, how much CO2 adsorbed. So they have a lot of methods can monitor that. So before we can conduct some the microcity study, okay, we have some other methods using traditional adsorption, deabsorption method to quantify this. Okay, so here we use the polar modeling because everything needs to be modeling and analyzed later for the reservoir design. Okay, so what do we have here? We focus on small scale as we said. Okay, so we don't talk about the upscaling issues, how to first full scale, life scale. So here we want to observe the mechanism from the pore scale. So we use shear pore lateral modeling. Okay, so with 3D imaging models generate the computation based on statistical approach. Okay, so we have a different shear fraction. We have low and high density of the shear samples generate polynomial modeling. Okay, so let me have a. So the right hand side, this is a low density fracture, and the bottom is a high density fracture. So they have a different composition, it's similar to the real shale sample. Okay, so shale polar modeling, what's the novelty of this one? Okay, so we try to build this is the first triple porosity shale polar modeling, so we consider swallowing effect. So this model can be simulated how the shale dissolved CO2, the swallowing effect. Okay, we have a triple porosity system. We have the mesopores, so inside shale with a micropores with meso salt and micro salt. Okay, as also a fracture. So that is a triple porosity that shows there will be similar to the real shale sample. So we contribute. Okay, so we have shale polynomial modeling. Fracture volume change to the swallowing and effective stress is the main equation. So how the swallowing stress and effective stress change. Okay, because as shale as we said, all the rock that fracture permeability is interesting because when we injection some the fluid inside, okay, we decrease the effective stress. Okay, in decreased effective stress means the fracture will be open. Okay, in the real reservoir, we injected something into the fracture. We can inject out of that. The effective stress will decrease, fracture open. But swallowing effect is a reverse effect because it's increase the matrix. Okay, so the fracture will be closed. One open, one closed. So how is it working? So they need to be detailed identified. Okay, through simulation. Okay, we have model verification from the former foundation experiment data. So we verified our model. So that is an example for how it's changed the different confining pressure. It assumes the different depths of the real reservoir. Okay, so here is the example. Okay, so that is the permeability change, how the permeability change. Here at the bottom, the injection pressure. Okay, right in the upper, this is high density fracture shield, this is low density fracture shield. So we can see the different injection pressure. Okay, we can reduce swelling first. Okay, if we continue injection, the back become mechanic changes become dominate. So we can see the permeability decrease first and then increase. Okay, this is the consistent with some of the experiment observation. Okay. Also, if we have confining pressure, lower confining pressure, so assume the shield reservoir is shallow, shield reservoir. Okay. In this time, okay, we only observe the swelling effect. We did not observe the mechanical effect due to the effective stress change. So all the permeability decreased in the lower confining pressure, lower left. So that is okay. So that is Polar global modeling. That's the dynamic effect. Until now, what we observe, the summary. This is swarming is dominant over all CO2 injection pressures in lower confining pressure. Okay, and the aperture size distribution consider stress change are more heterogeneous like. Okay, the average reduction in periodic size in low density fracture sample is started of the high density fracture sample. Actually, this part of the research already published, okay, in International Journal of Greenhouse Gas Control. If you are interested, you can come to this, okay? So we move to next one. We come back to the microcity thing, okay? Come back to the temperature dynamics reactive CO2 flow and trapping carbon rock, okay? So why we learned that? Because nowadays the people thought about we can inject in CO2 flow, inject into the abandoned oil and gas field. As we said, a lot of the current oil and gas reservoir, the carbonated reservoir, right? In some North Sea reservoir in Middle East, a lot of the carbonated reservoir, carbonated rock, okay? But the problem with the injecting CO2 with the formation water is from carbonic acid. Okay, the acid can eat rock. Okay, can eat rock. So that is a fluid rock interaction. It can change rock microstructure. It's very sensitive to the carbon reservoir. Okay, so the negative understanding of how the property of CO2 residue trapping change in reactive transport process. So the former people are doing simulation or something like that. They didn't consider about the trapping property actually changed due to the CO2 formation water. They eat the rock, we change the microstructure, change everything. So it means the trapping, the residual trapping, the capillary trapping already changed. So that is that. So we conduct this in the I-13 beamline diamond source. Okay, we saturate CO2 saturated flow. So in the anion sample, we conduct drainage imbibition test before and after reactive transport. So what do we have? They have a similar setup. We have very low flow rate, the capillary flow rate. Okay, we have injection pressure, confining pressure, 10 megbar, 50 degree. Assume that's 1,000, 2,000, 1,500 meter depth. But different flow for extra density. We compare the gas phase, fluid phase, right? We have the imagined resolution 1.6 micrometer projection, sample size. It's small sample, of course. So that's imaging processing, raw imaging, filter imaging, corporate imaging, I segmented to different phase. So that is what it looks like. That is the post-reactive evaluation. We have different time. Okay, we injected, continue injecting. This is monitor how the fracture change. We can clearly see here. It's the rock, the more porosity, right? The rock matrix be eaten by the carbonic acid. Okay, if they ate the rock, that is how does it change? Okay, that porosity and permeability, how the porosity increase, how the permeability increasing. And we use the polar modeling and we got evaluate capillary pressure, how the local capillary pressure change due to the sample change. Yeah. So also trapping efficiency, we compare the trapping efficiency for the different the imaging data. Okay, because we focus on we can know how the trapping efficiency we can see. That is the CO2 saturation. It's up and down, up and down. It's a more dynamic thing, let's say, and trapping efficiency gradually lower as we said. Also, the relative permeability is a polynomial modeling to evaluate relative permeability. So this relative permeability capillary trapping is based on polynomial modeling. We also conduct tests of COP refinery after we doing imbibition and drainage. Very interesting thing is your drainage test, the before with CO2 pore volume, 10 volume drainage injection, how the CO2 occupied the pore volume fraction. After that, it's interesting, we can see the CO2 cannot go inside other pore, mainly for cars on the main transport road. It means after the road is damaged, eaten by the carbonate rock, okay? When the CO2, okay, all this flow will only go through the damaged zone, okay, the wormhole, you can see the wormhole goes through that here. So no matter how much we injected, it all goes through that wormhole. It didn't gradually go through other parts. The inhibition is more interesting. After inhibition, we still have before still have the CO2. After that, it's all gone, injected or disappeared. So that is until our summary. So what we found from here is channeling effect and residual pore scale, pore structure challenges significantly influence permeability and capillary trapping dynamics. Pore network modeling simulation shows the capillary pressure and trapping efficiency have complex interplay between dissolution flow dynamics and pore network topology. And also the experimental results show that CO2 residual trapping could largely decrease, okay, after formation damage. So this will be, of course, that is the pore scale. And in the large scale, there may be happen with the re-sedimentation of the rock. It may block some road. It's more complicated, complex compared to pore scale. So need more investigation and how to upscaling. So that is what we do. So that is, thank you for the funding support, UKCCS of the Diamond, also Carnegie Trust, and Ross Authority, and PDDF, and our collaborators from University Leeds, Imperial College, and Manchester. So that is that. Any questions? Yeah.
Thank you. My name is Chibu from University of Manchester. I'd like to ask, you showed that when CO2 is injected in shale reservoir, there's a swelling effect. First question is, that is by what mechanism? Is there chemistry behind it? Is it because of precipitations of minerals that is in the shale? Or is it because of calcium carbonate precipitation?
No, that we didn't consider about here we didn't consider the geochemistry that affect, only consider simple physical phenomenon is the CO2 are dissolved into the shale matrix without swelling. So here we didn't consider about the reactive transfer flow inside the shale. We only cover the basic how the swelling affect the fracture permeability.
Okay.
So we didn't consider about that, but you're right. So we should consider about how to participation or some the reactive flow transport inside shale fracture, because there's still some minerals can interaction play with the CO2 formation brine, right?
Okay. With the physical process that you considered, was it for a long time or was it short-term observation?
This simulation should be because here we will see we have the injection pressure. This is a not dynamic process. Okay, this is we will injection this pressure. So this is looks like the end effect. So after injection as a 15 megapar, the injection pressure. So and after that we observed how much the permeability already, that is. It's not maybe sometimes it's not timing effect. Yeah. Yeah, steady state, but it's not unsteady state.
So question number 2, for the carbonate reservoirs.
Good day, everyone. I'm FM Gramina Hope. from Foodtech Engineering Limited. So I was wondering the imaging, like, did you use CT imaging to see what's happening in the pore spaces?
Yeah.
Pore networks?
We synchrone diamond.
Was it
I-
real time, like as the flow is going and you monitoring it real time?
Hmm?
Are you monitoring the flow, like the change in the rock properties? Are you monitoring them real time?
Yeah, real time. It's around the diamond is how much I got it? 10 minutes, 15 minutes, 10 to 15 minutes, 10 to minute scanning. So that is the faster here in UK. So that's the resolution. But if we in the future go to Switzerland, the Switzerland source is very fast. It's 10 seconds, something, half a minute. Yeah.
That's impressive. Thanks.
No.
Yeah. Good morning. This is Najat Rahmani on University of Bradford. So if you look at the 3D, can you go back? I'm just wondering how you recognize this is the calcite, the others. Have you done the SEM analysis? Just go back, please. Go back. Yeah. No, that's the next slide. Next slide.
This one.
Yeah. You say this calcite, right? Once you do the X-ray, normally you have.
No, this is not X-ray that thing. It's because the shell, that thing, if you use X-ray, you cannot see that because the resolution is nanometer resolution should be achieved. This is a static approach. It's from university needs, they generate a different shell model, static approach according to.
So how you recognize this is a calcite or silicate?
It's based on before you have a FIB, that imaging, other imaging, you can see in the nanoscale and use static approach to generate the sample. It's not the real sample. That is use static approach to generate the sample. Assume that it's a different.
But this 3D is reconstructed based on the some X-ray or other.
No.
MRI
This is not. No, this is not. This is not based on that.
So then how you find this 3D is created this?
This is based on the static approach. If I have the FIB imaging before, different FIB imaging, you can actually see what's the combination it is.
But you say this is a voxel 0.05 micron. Is
Yeah. This is a model.
solution.
This is a model, built-in model. This is not real from imaging to that one. That is we based on the experience to generate it.
Okay, good. Thank you.
Yeah.
I did many X-ray in the University of Leeds. You mentioned that time.
Okay.
I was thinking maybe something.
Yeah. So the next
that
step.
I'm not aware.
Next step, we may be using the nanoscale imaging to generate the shell sample to conduct the simulation to check.
A long running to be continued debate, no doubt. About what is real and what is a model. Right, thank you very much.
Thank you.
That's great. So we're going to stay with the
Let us go to the next.
micro scale imaging theme, I guess.
Yeah.
Kate Dobson.
Sorry. I
Kate
got
Dobson, preview of Kate's talk.
Okay.
Kate Dobson, University of Strathclyde, is reader in geomaterials and going to talk to us about imaging.
More imaging.
Yeah.
So yes, hi everybody, I'm Kate, I'm here at Strathclyde and I'm the talk today, knowing who I was going to follow, I didn't put too much of our science outputs into it. It's more of a intro to what imaging could possibly do for you and a shameless plug for the new imaging facility we've just got funded here, which expands on what Glasgow's got and provides some both high speed and high resolution capability that's available to all of you in the audience and people at the institutions and companies that you work with as a UKCCSRC funded imaging facility for national use. So today I'm going to be talking a bit about image-based solutions for CCS. We've already seen some lovely examples. And we've been talking about things that we want to do together in the future about on this sort of clever being able to exploit 3D and 4D imaging to understand the problems that we face. Because when you look at a 2D thin section, especially for something with a complicated porosity, the 3-dimensional porosity and the simulated on the real flow, we can simulate it and we can image it real time, is a 3-dimensional challenge. And any 2-dimensional section through that is a problem, isn't ever going to be fully accurate. So as the community in the room is interested in storage challenges, we have a multi-scale problem. We have problems and issues and impacts and effects that occur at the nanoscale, as we were just talking about, but in the shale system, up to the micron scales in the sandstone, the more porous systems, all the way through to trying to simulate these problems on a reservoir scale. So how do we take a core and actually understand what the micromechanical, microchemical combination of reactions is going to be on a macro scale? How do we upscale? How do we downscale? What is the key parameter in spatial scale and temporal scale that we're interested in? We're interested in the evolution of porosity and permeability. We're interested in faults and fluid flow and fluid rock interactions. We're interested in mineralization and how those minerals change through time as we are going to do stuff to our reservoir or to our storage system. We're going to be either changing the fluids that are in that, increasing the pressure. What's that going to do to the system we're looking at? And we work on the micro scale, on the macro scale, on the reservoir scale. This is lifted straight off the UKCCS website. We look at the core scale, at the meter scale, the unit scale, what's happening around a well on that kind of initial injection scale. This is a picture of one of my PhD students' theses about to be submitted. So, on the unit scale, how do we simulate that? How do we understand what's going on those kind of scales, on the scale of a fracture, on the scale of an injection point, what happens around that point? But actually what's controlling those meso and macro scales is the stuff that happens at the pore and individual surface scale. How do we trap the system? How do the fluids actually interact with the systems? How do they get trapped? How do they move? So what we're interested in understanding is how those three scales link and how can we get the data out? Often, whatever scale we're working at, upscaling or rescaling to the other one is the challenge. And that's where imaging has the potential to make some difference. We're not just interested in the storage media. We've already heard a bit about it today, what's in the overburden, what's in the wells, how is our subsea and well civil infrastructure, the casings, how is that involved with the system, how is the behavior of those civil infrastructure components affecting our system and how our storage potential is being affected. So we've got a lot of complicated things in there. We've got the rocks, so our storage medium for most of what we're looking at is sandstones and equivalents, carbonates perhaps. We've got the concrete and the steel that are in civil infrastructure. We've got the fluids that we're putting down and the fluids that are already down there. We've probably also got the microbiome that's down there as well in some cases. How are all these things interacting? And some of the processes and challenges we need to think about in these are also things like corrosion and fatigue, as well as the precipitation, dissolution, and the trapping aspect of this, putting the CO2 down into our storage systems. So as an imaging person, and I'm a geologist by background, but I've been playing around in the 3D and 4D imaging space for about 15 years now. It's a very long time. We're interested as geologists and as people interested in the CCS space, we're normally interested in how those micro scale and macro scale processes link and how do we understand our systems so that we have an understanding of the millimeter to microns, nanometer to micron to millimeter scale processes that we can use to predict real world behaviors. And that might be empirically, it might be numerically. We have people that focus on the modeling, we have people that focus on the experiments. How does what I do at the micron impact onto what other people are doing on the reservoir scale? We need to understand all of these challenges. And we're trying to understand a range of different processes that operate over different temporal and spatial scales. This is a generic one for sort of most geo processes, but most of it's applicable for carbon capture as well. We've got a range of different processes that operate over from the microseconds, how long does it take a fracture to actually propagate in a stage, all the way through to things that operate over years, millions of years, when we look at carbonation, mineral alteration processes, depending on the temperatures and the fluids involved. And over a range of scales from, surface interactions at an individual point, the behavior of an individual pore at the micron scale, up to centimeter, the unit, the rock, the reservoir, all of those scales. So we're working over several orders of magnitude in time scale and several orders of magnitude in spatial scale. Who said geology was simple? So where the imaging comes in and the work I'm going to talk about a bit today is kind of on that shorter time scale. It's very hard to do experiments over more than a few months in the lab. The longest experiment I was ever involved with as part of a long-term leaching experiment was 9 months, and that was a very long experiment by the literature standards. It's also hard to image rocks accurately when we're looking at very large features, because we're interested in the smallest features within them. We image a large rock, we can't see the smallest things within it. So again, it's that scaling issue of what can we image and what can we see and what can we understand at what scale. So we have a range of different techniques. Some have already been mentioned, others will come up over the course of the sessions. And what we're going to be looking at today, and what we've already heard a bit about, is the CT, but there's a bunch of crystallographic, chemical, and imaging in 2D and 3D that we throw at our samples to understand them at the micron to millimeter scale, generally speaking. But some of these will go up to the meter scale if we want to. We can push to the meter scale if we need to. What we're interested in this room is how is the sample we're looking at, how is that material formed, and what we're going to do to it, what is putting this carbon dioxide into it going to do to it, how's it going to evolve, what is it going to do, how's it going to respond to how we use it, especially if we're changing the use of it from what we've done before, so reusing and repurposing depleted reservoirs, for example. 2D data aren't good at capturing 3-dimensional and especially 4-dimensional processes. We've already seen a little bit of that earlier. And our materials are often changed by how we preserve them and how we prepare them. For most of us who are working on subsurface samples, they've already been brought to the surface. They've already been depressurized once. One of the issues we always have with shale samples is how is the microfracture preserved from what was at depth to what's at surface. So how do we do some of these issues, and how do we deal with these things in terms of how do they affect the performance? And most of us are normally interested in the process that's happening as much as the output of that process, the product we're doing. We want to know why and how it does it rather than just what it does. So tomography works by doing 3D imaging. I'm not going to go through this. We've already seen some pictures. We take a set of 2D images, we turn them into a 3D model, and we can do the quantification on that model to understand the objects, the features we're interested in. What we've just put, or what we're in the process of installing in Strathclyde now, is the images facility. And this is a snapshot of all the different capability we've got at Strathclyde, which allows us to go from imaging, can take 4 hours or more for some of the more high resolution, more advanced techniques. We've got a phase contrast and diffraction contrast capability with our new system that's just been installed today, or it's being installed today. And we go all the way from high resolution at lower speeds through to lower resolution at higher speeds. And in the previous talk, you heard about synchrotron imaging, where we could image a sample in 5 to 10 minutes. Our new test scan system would be able to image the same sample in under 5 minutes and probably under 1 minute for some applications. So we're being able to push that temporal resolution much more, which allows us to do much more clever science in terms of understanding the dynamics, especially of poor scale flow processes. So in terms of how we use this for CCS, we use our 3D data to get an image of what's actually in our samples. We can do before and after imaging, which we've already seen a little bit of today. We can do imaging during the experiments as well. But we can start to take that real data into the simulation space, and we've been playing around with this at Strathclyde and with collaborators for a while, looking at basalts and thinking about carb fix and CCS trapping from that perspective. So we can simulate how much of the volume we can image, how much of the volume is accessible to the fluids. We can do clever simulations that then look at the temperature and the reactive transport and how much of the carbonate, how much of the volume can be impacted in the carbon, can be affected and react with the carbon CO2 that we're putting down there over time. So we can do the simulations. This is some work from former postdoc of mine and collaborators at other institutions. So we can take it into simulation space and re-precipitate. We can numerically precipitate the carbonate, or we can numerically erode the carbonate that's already down there to understand and backstrip effectively the pore filling phases that are in those rocks today to see what that resolution and what that permeability, porosity structure was like in the past. We can do it when we're doing reactions. So this is some work from one of my former PhD students looking at imaging before and after the experiment while we're seeing chlorite alteration from bertharine to chlorite or chlorite to bertharine, seeing how that changes the openness of the pore structure. We see a large reduction in the porosity, but we don't actually see a change in the permeability in this sample because of the structure of the material that's altering. It props open the porosity. So we can see changes at the submicron scale. These were 1 micron resolution data sets, and we can see texture. We can see hints and information about the texture at submicron resolution with 2D on these samples after the fact, to understand how those textures are evolving through time during experiments. This was looking at, these are high temperature, high pressure experiments that we are running to do these alterations. And we can take it even further. This is nanoscale data from the Manchester group. This is actually looking at corrosion in a metallic sample, but it's a system that we would see in some of our civil infrastructure to do with wells, where we can actually do nanoscale time series imaging and watch the structures and the particles and the objects in our materials change through time. This is looking at corrosion, but they've done similar kind of studies looking at fracture propagation, precipitation at the nanoscale. Nano lab scanning goes down now to about 50 nanometer resolution, but the amount of material you can image that resolution is, of course, very small. So it's hard for geomaterials, but it's more applicable to some of the man-made materials that we put into our storage systems. So that's going down in the resolutions of what we can see. We can take those models, we can take those 3D images that we actually have of the real porosity in our systems and use them to validate the numerical systems that we work. Most numerical models are developed on very simplistic pore structures, which aren't necessarily realistic for the real pore structures we've got. So there's a string of work going on by many people across the community looking at how we can simulate, how we validate our simulations against real systems. This is some of Phil Salter's PhD work looking at flow simulations during a carbonate precipitation process from the beginning on the left to the end on the right, where we can see the changing as he precipitates the carbonate, it changes the flow speeds and the distribution of the flow through the system. And we can do the similar thing with the basaltic samples at the top, where we've got a larger scale porosity to understand how flow occurs and changes through time in these samples. Testing the numerical models against what we can see in the lab and using real structures to test them. And then we can do simulations. This is some of the work of Lynn Ma from Manchester's PhD, what I was involved with back when I worked down there. We can do the simulations and do the flow simulations through these and understand how things are localizing, where things are localizing, and get to some of the mechanics and processes of why. We can move that time series forwards. This is some work from the Ghent group looking at understanding fluids in the system. This is similar to the work we've already seen this morning, looking at where the fluids are and what they're in contact with, understanding contact angles and surface curvature of the interfaces. What's the wetting phase? Where are the wetting phases? How are things changing as we pump different fluids into our systems? We can now also do this under load, so we can fracture our systems whilst we're imaging them and flowing things through them. So we're getting to the point of actually being able to replicate fairly realistic subsurface conditions. This is what you get when you get to high-speed video of these kind of images. What you see here is the fluid coming in 2D here on the left, and then the 3D pore rendering on the right, showing how that pore moves through the system, or how the fluid moves through the system and invades individual pores or replaces the fluids in individual pores. And when we look at that, we can actually put tracers in, so we can then actually start to look at the porosity and the flow networks, and we can then track each one of those particles to understand the fluctuations in the flow field during the perturbations. Again, this is the Ghent group. This is a recent study looking at particle tracking for this, which allows us to see those dynamics. We can't yet quite image fast enough to see individual Haynes jumps happening, but we can understand the flow processes either side of those Haynes jumps. The same with a fracture. We would struggle still yet to see the individual fractures, but if your sample is not substantially ductile, you can image fast enough to actually capture the fracture propagation and the fluid movement along those fractures in real time. So there are a number of different resolutions and a number of different scales of which the Images facility can try and tackle. And we're already working on a bunch of CCS related activity, and we're more than happy, and the facility is available for all of you to come and work with us to solve your problems in these spaces. And I'll leave it there. Thank you very much.
Great, thank you very much, Kate. That's an impressive set of movies as well. Get better every year.
I kept them to a minimum.
Well, I'm sure we can watch movies of pores all day. Anyway, questions, anybody? Comments? Requests for help? Yeah.
Thanks. Hi. Adrian Topham, Crown Estate. Thanks, Kate. Really interesting presentation. I guess my sort of thought was, how is this being, what proportion of requests are you seeing, and it's probably early days, for mechanical type work to do with construction and civils, as you put it, versus geological effects?
The geoscience community are probably adopting it faster than the civils community, but the material science community are at the forefront of it. So the geologists are a bit late to the party compared to material scientists, and the civil engineers are only really just getting going. But that's mainly because the technology advances. So the sensitivity of the lab sources to the subtlety of the mineral changes in concrete is only really just getting to a point that's useful. It's a bit like when tomography first came out in lab sources, the paleontologists could use it as it stood because it was good for fossils, but it was hard to do proper rocks, or non-fossil rocks. In the same way, because it wasn't quite as sensitive. So the technology jump in the last decade has been huge. We can now do in the lab speeds that we would have to go to the synchrotron 3 years ago. The experiment you showed on the I-13, we can pretty much do in the lab now. Maybe not under exactly the same conditions, but there's a huge capacity. We've already got 4 or 5 projects in the pipeline from this community coming through. The machine is still being installed. The engineers are on site today doing that. So we've already got some input, but we're more than happy to chat and we can help you design your experiments. We've got the flow cells that are available to the community to use. One of the challenges is doing it when you don't have the kit at home. And that's what this facility is trying to do, is to enable everybody else to have access to more of the high-end kit for our research. Shameless plug.
Thank you for your nice presentation. I'm in from University of Glasgow. I have some questions about the modeling part of your work. I'm curious of what was the numerical platform you used for your simulations, because I saw you had high flow rates, 1 milliliter per minute of your injections. I'm just curious to know if you simulated drainage or imbibition or both. I'm not sure. And I'm asking about your numerical platform because in our study we are focusing on portal fork models, and portal fork models to date cannot handle very well high flow rates, the dynamic effects. And I'm curious to know how we, in your numerical platform, you could consider phenomena like Haynes jumps or any other pore scale, multi-phase processes. Thank you.
The experiments I showed with the highest speeds are dynamic, real experiments. You're not seeing a model, you're seeing the motion of every particle trapped through that space. So simulation at that scale is challenging. We're not at that point yet for the very reasons you've registered. Generally speaking, our focus at the Images facility is getting the data that allows you to get the empirical, that allows you to then find the model that works. We use the appropriate modeling tool out there, and that's normally shaped by our users in terms of their application. So there isn't a single answer to that. For the crystallization, we're generally doing it numerically in the imaging space. So we grow by increasing the number of pixels of an object in a particular way. And we can link that to the simulation of the flow, which is normally, we've got a combination of lattice Boltzmann and normal Darcy-Naylor-Stokes flow models that we use through these structures. It depends on the complexity of the system and the problem we're trying to tackle.
Okay, so the simulations were actually captured capillary dominated flow.
Yes.
Okay, thank you.
I think we're probably out of time. Has anybody got a quick extra question? Short question then.
Yeah, thanks for the presentation. I wanted to ask, what's the maximum duration someone could use your facility for their experiment so they know how to plan the design?
So we will be operating a free point of access scheme for new users and pilot data that people can apply for. That will probably be capped at about 5 days of time. But if you're putting it on a grant or a larger project, come and talk to us, so you can put on as much time as we have capacity to take. So we are expecting experiments that are days of time in a block. We are also expecting experiments that require the long-term repeat access once a week, once a month, to track those slightly slower processes that we can't get to any other way. We can accommodate both. But come and talk to me and we can help you design your experiment to fit what availability we have.
That's great. Okay, so a whole new world opening up there. Almost free of charge. Right, thanks, Kate. And now move on to Aaron Cahill from Heriot-Watt University, who is part of the assistant professor, if you like, at Applied Geoscience, and is going to talk to us about, well, borehole containment and CO2 containment in particular.
Indeed I am. Thank you very much, Stuart. Just see if we can find my
Don't touch anything.
Don't touch. Don't just the clicker. Just the clicker. Let's see. Here we go. All right. Just the clicker. All right, thanks very much then, Stuart. So going to switch gears a little bit now compared to the other talks. So we're in the storage session, and what we're going to talk about now is a bit more kind of risk-based, looking at risks to storage, risks of containment with CCS. And what I wanted to kind of walk through you guys is some work I've been doing recently on legacy wells and CCS and how we're trying to understand the risk that legacy wells pose to CCS containment and how we're going to try and manage those risks to storage. And first, where we need to start really is to kind of recognize that a little bit of an elephant in the room when it comes to CCS is that when we're going to store carbon dioxide into the ground, typically where we're doing that is where we've developed petroleum products before, hydrocarbons, because we know there's good trapping structures, so on and so forth. But that means that we're doing this where there's old infrastructure, old legacy wells. And if you look in a kind of rough manner, you can kind of look at around 150 years of development, during which there's around probably north of 10 million wells globally have been drilled throughout all these different basins, which will be used for CCS. And obviously the plan here is that, of course, we plug and abandon these wells is the ideal, and that they're then decommissioned and sealed, hopefully in perpetuity. Here's a little example of one of these legacy wells. This is Hardstoft #1, apparently the first oil well drilled in the UK from 1919. It's about halfway between Sheffield and Nottingham. It's actually apparently now it's in a garden centre, and people go and have a look at it. And there's actually signs, of course, you can see some sort of fluid migration still coming up from that old well. So why am I so kind of interested in these legacy wells? Well, if we think about net zero and future use of the subsurface, we want to be doing lots of low carbon, no carbon activities such as CO2 storage, maybe hydrogen storage, geothermal, for example. And all of this will take place in and amongst these legacy wells. And so it's about understanding what the implications are of those legacy wells if we have failure or leakage along those wells for those technologies. Just to jump straight to the point, legacy wells do, in certain situations, suffer integrity failure and leak. So there's lots of documented cases around the world, particularly in North America, particularly onshore, but also offshore, to just get to the point where we can say that this can happen, and we need to kind of understand it a bit more and look at what it means and how to manage it. It's a really, really interesting research topic. It's kept me busy for about the last 13, 14 years. Because it's a very applied topic and there's lots of different aspects we need to look at and understand, and all of these aspects really do need better understanding. Everything from the wellbore engineering, why a well structure fails, how it fails. We need to then look at the multi-phase flow of a fugitive fluid as it leaves that wellbore or moves along that wellbore, all of the interesting stuff we heard about from the previous talks at that pore scale up to the larger scales. There's lots of reactive transport. The bugs and microbes in the subsurface also start to get involved in that as well. And then at the very top of the system, we ultimately can have emissions out from the soil, shallow soils, and then we get lots of cool stuff going on where, for example, climatic and weather conditions control what we actually see coming out of the ground. So really, really interesting and fascinating topic, which you can really get your head stuck into. Key questions that I'm trying to look at, and lots of other colleagues of mine are trying to understand around legacy wells. The big one at the moment, lots of people are trying to understand what the implications of integrity failure of legacy wells is for CCS. And within that sort of overarching question, there's a few sub-questions. How many legacy wells suffer integrity failure? How bad is that failure when we say failure occurs? Is it large levels of leakage? What kind of volumes and magnitudes are we talking about? And then, of course, we need to try and manage and mitigate that issue rather than just kind of, you know, bury our heads in the sand or run around with our heads on fire. So what can we actually do about this to kind of minimize the risks to CCS containment? And I've got a few different projects I'm working on at the minute. I'm going to kind of work you through a couple of the most interesting ones which look to answer those questions. So firstly, when we really want to understand about legacy well integrity, we need to go into the field and look at these old wells. They're real, they exist. We go out and we have a look and we try to understand if leakage is occurring. So a recent project I was lucky enough to be leading involved looking at 10 representative P&A wells in British Columbia, Canada. So these were actually relatively modern wells, typically 10 to 30 years old. Quite a few were actually unconventional configurations, but you'd term them modern well designs. And we go out and we do some rigorous field investigations. There's a table there with the wells anonymized A to J, 10 different wells with some different characteristics of those wells. And if you look at the map there of Northeast British Columbia and Canada, that's quite the Swiss cheese up there, where they've done a lot of development. It's about 25,000 wells since the 1960s. So this is described in this paper from a couple of years ago now. I'll just kind of work through the key results. So what do we do when we go out in the field? Well, we take a bunch of equipment out. We monitor the climatic parameters, wind speed, barometric pressure, temperature. We take some greenhouse gas analyzers. We take flux chambers. We poke around in the soils around the well. We take some samples. And we take some soils and also soil gases and send them to the lab to try and understand if that given well is exhibiting signs of integrity failure. There's a range of conditions in the field when we do these investigations. So sometimes we're in a nice grassy area. You can't even see there was a well there, but it's buried, capped and buried under the ground. Sometimes it's very recently abandoned, and you can still see where the well pad was. At some of them, we even still have a wellhead which hasn't been removed yet, and sometimes the farmer is growing some wheat in there. So quite a range of conditions. What did we see when we visited these 10 wells? Well, here's some flux footprints for methane and CO2 fluxes measured around the wellhead. And to cut to the chase, out of the 10 wells we examined in this study, 5 had signs of potential leakage from those wells, which was manifesting as co-emission of both methane and CO2. Methane is typically what we're looking to see and detect here. And so why was the CO2 coming out as well? Of course, there was reactive transport of the methane, and it was degrading a CO2 via the soil microbiome. So we get this co-emission. And you can see a table there where actually we do these flux footprint analysis. You can get some absolute values, estimates for total emissions. So 5 out of 10 had signs of leakage, but what was interesting was the leakage was very low. So if we look at the highest leakage value was well site J, was just under 2,000 kilograms of CO2 equivalents a year. And if we compare that to what is typically referenced for what a CO2 equivalence of a single cow might be, it's about 8,000 kilograms. So these are all way less than a cow. So double-edged sword, 5 out of 10 potentially leaking, the leakage is very small. So this well site J, the one what was leaking the most, this became very interesting to us, and we wanted to follow up. We've been back a few times. In fact, I'm going back to visit it in about 3 weeks' time with a student. This is what well site J kind of looks like in that landscape. You can see lots of old legacy wells there, well site J with the star, and we've got lots of information on the well in terms of the construction, when it was drilled, so on and so forth. And we see this really interesting co-emission of methane and CO2. Again, we just had another paper out where we go into more detail on this well. You can look up more details if you like. This is what that well looked like. It's the wheat field. The farmer's quite happy growing his wheat there, even though it's leaking. He doesn't even want anyone to do anything. He doesn't want them to bulldoze his field down and go back in there. So we're actually looking at, is there any need to actually intervene with this well? Because the leakage level is leakage, but it's quite low. And when we've gone back, we're now getting more measurements where we're able to look at how that leakage is varying with time. Each year we go back. This year we're going to get more and more measurements as well. And we do some more of these kind of superficial leakage footprints analysis. And again, we're able to come up with estimated leakage rates along the well. And also we're looking here at modeling of the methane oxidation through the soils. So we've been playing around a bit with looking at this co-emission throughout the year. The temperature influences the oxidation rate. And you can see we can start to try and predict how much methane is being oxidized and what you would see coming out of that well. So lots of good information here from this kind of living field laboratory, helping us understand leakage. And then we can try to use some of those learnings to understand risks to CCS containment. So quickly move on to a couple more projects where we then look a bit more at legacy wells in a direct CCS context. As I mentioned, there really is a need to manage this as a risk. This is accepted and acknowledged as quite a big aspect to understand. I know lots of projects that are spending quite a lot of time and resources to understand what legacy wells are in their domain for CCS and what those wells look like and what the risk might be associated with them. Typically, any CCS project might look a bit like this, where we have this inset map, where we have a domain, in this case offshore, where we want to do CCS, and there's lots of old wells. We have an area within that where we want to inject our CO2. We get to this kind of cube of the subsurface where in that CCS area, we're going to have further still some legacy wells of different ages, different configurations. Some might be vertical, some might be have horizontal or deviated sections. Some might have been appraisal or production wells. And so it's this kind of common problem we're seeing across CCS projects is how do you deal with this in an effective way? How do you screen at a higher level to help you narrow down which wells to focus on and understand a bit more? And again, just another little paper if you wanted to read all the details. I'm only going to run through this really quickly. So PhD student working with me, Benjamin Pullen, he's just published in Greenhouse Gas Control Journal, where what we did was used a multi-criteria decision analysis framework to help try and screen and score wells to indicate potential risks. So here we're trying to identify wells of the potential greatest or least concern in an area and to try and prioritize any monitoring or evaluation of those wells as kind of a decision aid tool to help us evaluate what an area is like for risk from legacy wells. And this is the classic kind of MCDA framework where we have different data sets. We have geospatial information, temporal data, and engineering data on those wells. And we pick out parts of that for each individual well and come up with some form of score to help indicate the risk posed by that given well. This shows the Scottish North Sea context and why we want to do that, because at the most basic level, we have a map full of dots, red dots, which isn't particularly helpful because all of those dots are very different. They're very different wells, different ages, different depths, so on and so forth, different characteristics. And so what we're really trying to do is say, can we move away from just this generic dot and come up with a way to look at ones we might be more or less interested in terms of containment risk for CCS. And so what we did with our MCDA approach was we found all the parameters, what was easily collated data for across that data set, that domain of wells, which were seen or proven in the literature to be linked to integrity failure risk. So they looked a bit like a little table on the side there. And we wanted to then weight those for which were the more and less important. And we did that via an expert survey where we had about 50 global experts answer an online survey, ranking and giving us feedback on what parameters they felt were most or less important for what could lead to integrity failure in a well. And just given there some little demographics of the people who answered, I think more than 70% of those 50 people had a master's degree or above and more than 15 years CCS direct experience. So hopefully a relatively knowledgeable lot. MCDA, in this case, we just used quite a simple linear weighted score approach. And what you're able to do in a real simple way is come up with a score for each well. And so just as an example, without going into all the details, here's some of the most pressing or currently considered CCS storage sites in the Scottish North Sea, for example. And instead of having them all red dots, we're now splitting them out into a little bit more of a traffic light system where we've got blue ones, which kind of fall in the middle. They're neither showing traits of particular risk or not. But then what we're mostly interested in is the reds and the greens, which have some of these traits, which make them either much less likely to have integrity issues or much more likely. And so we can just start to then pick out where might be of more interest to look into, or what wells can we kind of narrow down to consider. So if you want to see a bit more, find the paper and have a look. And then last but not least, on my little whistle-stop tour of legacy wells, just to mention here a little project we've had funded for the last little while from UKCCSRC flexible funding, is that now we've identified perhaps these wells we're most interested in because there's perhaps risk around integrity and loss of containment. What do we do with that information? Well, we want to then look at maybe estimating leakage potential or understanding what under different conditions or different boundary conditions the leakage might look like through those wells. And so in the UKCCSRC flexible funding project, we're called Q well rate. We're looking at developing quite a simplistic legacy wellbore leakage estimation tool, which is basically a simple steady state non-isothermal reduced order wellbore model. Working on it here with a few colleagues. I'll acknowledge everybody at the end. And you've got this kind of classic simple conceptual model where you've got a CCS reservoir, you've got a potential leaking legacy well, which has a specific configuration which we can put into the model, and we can look at under different boundary conditions what type of fluid flow rates can move through that. So as I say, steady state flow, it's a worst case scenario tool. In some ways, it looks at what would be a sort of your conservative, most leakage could come out. It's a quick estimate, accounts for parameter uncertainty, and it's been developed by in the Julia programming language to make it open source with no license costs. And it's very, very rapid. So this is definitely an abductive, heuristic, simplistic, reduced order model. And what we've been doing at the minute, the project's still underway, so we're not done yet. Watch this space. Maybe next time I'll show some more detailed results. But really what it can do, it just starts to give you leakage rates, estimates in, for example, tons a year for different scenarios. So here looking at different reservoir depths, for example, or looking at different reservoir pressures, different changes in permeability through the wellbore structure, and different pathway radiuses. Another little feature we've been developing as well is to then look at generating leakage heat maps, so different areas based on reservoir depths and sea column depths. For example, in the North Sea, you can actually start to then map where more or less leakage might occur through different legacy wells if there's failure. So it looks a bit like this. All right, so that was the whistle-stop tour. What are we're talking about CCS, we're talking about storage. What are the implications then of these legacy wells? Well, here's kind of some musings from all of this work I've been doing the last years. Definitely legacy wells are a major risk factor in CCS applications. I know lots of projects are having to really spend a lot of time and resources on considering legacy wells. I've heard people talk about them being potential showstoppers, in fact, with projects. Basically, for me, looking at this for quite some time, we really don't understand all of the ins and outs of these legacy wells. We don't know how commonly leakage occurs. We don't know why. Longer term integrity is even a greater unknown. So, okay, even if a well's not leaking now, what happens in 50 years, 100 years, 1,000 years? Do we start to see leakage, and how does that kind of play into it? Overall integrity of these wells is difficult to predict, challenging to detect, hard to understand, but we do have to try to enable these CCS projects to go ahead with minimal risk. And that double-edged sword, I think, is a key take home from a lot of this work, is that whenever we look at, the more we look at wells, the more we find leaking, unfortunately, but also that leakage does tend to be quite small. So it isn't the end of the world. It isn't necessarily a showstopper. It's more about expectations. And I know there's lots of discussions around what could be acceptable containment degrees for CCS. Is it okay as long as 99% stays in the ground, or 98%? I think we need to be a bit more thoughtful around that, and accept that even if there is small levels of leakage along a legacy well, it still has a net benefit, that project overall. It shouldn't necessarily be a showstopper. So I think that was everything from me. Lots to do in the coming years. We're certainly not done on this topic. Massive kudos to all the colleagues helping here. Ian sitting up there, for example, and Morteza from Heriot-Watt, Jordan Van Bessau from the regulator, and a few students there, James, Ben, and Hari, who's our architect of our Q well rate model, and lots of people who have helped this tick along. So with that, I'll be quiet and see if you've got any questions.
Thanks, Aaron. A macro talk rather than a micro talk, so quite different. Anybody got now questions or comments they want to ask? Yeah, I'll come in a minute.
Harry Vincent, British Geological Survey. Thank you very much for an excellent presentation. Really interesting topic, legacy wells. So for the UK, what do you see as the key regulatory barriers? What do you think is the next steps in terms of preparing for large-scale CCS? If we think there's going to be small-scale leakage, what do you think we need to do in terms of preparing for that in a regulatory way?
Yeah, really, really good question. Thanks for that. I mean, yeah, that's a tough one. I think we're not necessarily all on the same page in this topic. So as I mentioned, like this work in Canada, that's definitely accepted there as an issue to be managed and solved and dealt with. It's actually less accepted as actually being a problem in the UK. So we've been interacting with the NSTA. The reason being there's not really been much work done to evaluate offshore integrity of wells. Obviously, it's much harder it's much easier to drive with a pickup truck and put your equipment around. You know, there's not really been many studies offshore, so I don't think we really understand the integrity status of wells accurately. There is a feeling that there is no problem, particularly in the UK. This is the impression I get, which I'm not sure is the best way to be that confident, because everywhere else you go, around the world, and there are different regulations in different areas. And I've had comments before that places in North America are the Wild West and they did things differently, right? And we do things better here. But I think everywhere else you look, you do see legacy wells, unfortunately, in rare or maybe not so rare levels, suffer integrity failure. So I would be really surprised if we've done everything perfectly in the North Sea. I hope we have. But yeah, I think the first step would be maybe to understand a bit more the integrity status of wells in the North Sea, and then come up with robust ways to then manage that issue. But yeah, I think we're really at quite the early stages, and yeah, I'm not sure. We need some more work for sure. But that's a classic researcher thing to say, right?
Yeah, thanks for that. I agree with you that kind of expecting perfection could make it a showstopper, whereas having realistic expectations could allow us to move forward. So thank you.
But obviously that's a massively sensitive topic, isn't it? To say that is, and talking with the regulator, we can see the sensitivity they're having to manage right around that. So yeah, I don't know what the answer is, but we can only go out and try and get some data out there to help people raise the awareness, right, in a way. So anybody else?
Yeah, so I'm at the back here and I can pass this down to whoever wants to speak next. Sorry, I got really dead leg, so I needed to stand up. So my question is, do you know what the subsurface pressure conditions are like in the wells in BC where you've been looking at? Because I guess what's interesting here is you've been looking at, legacy wells that are now not pressure supported and so on. That's very different when you're talking about injecting or legacy wells when you're going to be perturbing the pressure down well and so on. So what do you know about the subsurface conditions for the wells that you've been looking at that are leaking, and what do you think that, can you really say that a well might not be leaking very much when in the future when you're going to be increasing the pressure in the subsurface?
That's a really, really good question, Jen. I think so. We probably can know we've got some data on some of the downhole conditions, not currently. I think that is a challenge because you can see that's in a field that's cut, capped, and buried. We probably need to look into that a bit more about what is, if there's nearby wells. We haven't. It's more been we've been so interested in just seeing what there is. A, there's leakage, and then B, how much is coming out. But we need to dig into that. But you're absolutely right, because of course, if you changed, a well might not be leaking just because there's a pathway, but there's no pressure. So yeah, I mean, really good question. And this is something they're definitely grappling with in Canada as well, where they're now considering onshore CCS in some of these areas. I guess we'll see, right? Like if people get going with it. But yeah, really good question. We should look into that more.
Hi. Hi, Harsham Mohammed from DESNES. So have you looked at any wells that have historically had CCS kind of injected into them? In Canada, there's certainly lots of EOR, especially in Alberta, where you've got the Alberta Carbon Trunk Line. Have you seen any difference in leak or potential containment issues from wells that have, had that CO2 kind of injected in to give a better idea of what a CCS well might look like in the future?
Yeah, good question. I mean, yeah, the point you're making obviously really well is that CCS is going to be this is the wells, what we found leaking. I mean, they're old wells, they're leaking methane. There's no CCS going on. Once you get the pressures involved, once you get maybe CO2 further degrading, if there's already weak points within a well system, you definitely could even have more impacts and changes in what we see. And so we need to understand that. I think we're not really fully at scale underway with CCS, are we? So I guess time will tell how this kind of plays out and what it means. But yeah, I mean that we just don't know, I guess, how it'll work. I mean, some people talk about even potential self-healing. I know some people working on things like Portland cement, if you CO2, that they hypothesize that it might even self-heal with precipitation and things like this, right? Or other people say you'll get obviously further degradation and maybe you can lead to massive further failure, and you start to get massive leakage. We just don't know. People model it, people are trying to understand it. We'll know when we really get going, and hopefully, we can minimize and mitigate it.
Thank you very much, Aaron, for your presentation. My name is Brian Allison. I'm ex-DEC Bays, and which has now become DESNES, but I've left before then. but of the Open University. It's not really a question, but it's more of a statement. Having worked with many energy ministers over the years I was working in the government department, two of the ministers, the very, very first question was, doesn't it leak? And I think it's having good answers for how to mitigate that particular question in such an important environment of having an energy minister who often needs to be put right.
Yeah. Okay. Yeah. Just I'd add a little comment as well to that would be some other work I've been involved in as well. Actually, if you look at these well systems, we should totally expect what you'd call low-level seepage. There's big discussions around leakage versus seepage, and some of these wells, really low level, it might be what you call seepage. We should expect they're not perfectly, completely low, no permeability systems. There's always a permeability. There's always, it forms a bit of a pathway. So again, it's that expectation is, I don't think, aiming for zero leakage is probably setting the bar pretty high. And that's how you term it around things like leakage versus seepage. Like some of these wells, maybe you'd term it seepage, which you're almost expecting to happen actually. So then that changes it, right? You're still getting 99.9% containment, but you're accepting that you should expect some seepage, for example. But yeah, we need to think about how we kind of describe everything, and that's really sensitive for sure.
Yeah, I think that's a good place to finish, is defining the terms. So that's time's up, time for tea break time. Thanks everybody, thanks to the presenters, of course.